Hello guys, I hope all of you are doing well. In this video, we are going to discuss our question Trapping Rainwater 2. Also, if you have not watched Trapping Rainwater 1, I first recommend you to go watch that video before starting this video. Now let's discuss our question. So the input in the input, we are given a 2D matrix that represents height of each cell, right? Its elevation. We are required to find how much total water will get trapped after rain. Okay, let's further understand it. So we are given a n cross m 2D array, right? So rain happens just like that, and of course water gets trapped, right? It's a 3D figure representing the same matrix. Okay, so of course water gets trapped. So we are required to find how much total unit of water will get trapped. So that's our task. Now, if you are watching this video, I am making sure that you have already watched Trapping Rainwater 1. If you have not watched Trapping Rainwater 1, go watch that video first and then come to this, because now we are going to discuss Trapping Rainwater 1. So what we did in Trapping Rainwater 1, let's see. In Trapping Rainwater 1, we were given a 1D array, right? So let's say we were given an array 2, 6 and 4, right? So let me draw the illustration. So let's say this is your bar chart. It is representing your height. So 2, 6, 4, right? Also here, let me take one more. That is 4, right? Okay, 4, 2, 6, 4. Let me building 4. Okay, so this is our bar chart. Here the height of first is 4, then 2, then 6 and 4. Also let me write the indexes here. Okay, so this was your 1D array, right? Trapping Rainwater 1. So how we used to calculate the amount of water you can store? So first let's talk about the boundaries. Can we store the water in the boundaries? No, we cannot, as there are no buildings, no elevation to hold. So in the 0th index we can't hold. Now let's talk about the first index. So what was the formula to calculate how much water you can store here? It was simple. Minimum of left max, right max minus my own height. Okay, so let's try to execute this formula. So here in the first index, our height is 2. So the minimum height, the left max is smaller than right max. Okay, so what will be my amount of water I can store here? It will be 4 minus 2. That is 2. So that means here its height is already 2, right? So here I can store more 2 units of water, right? Now, at the second index, can I store water? No, I cannot, as there is no left max, right? And no right max. And for the boundary, of course, we cannot store. So here the answer is 2. Now, you must be wondering that by using the similar formula, we can solve our 2D matrix. What the difference is? This time we got a 2D. Is it that simple? Let's try. So let's see. So what the first thing people think that earlier we were calculating left max, right max, right? So this time we will calculate top max, left max, down max and right max, right? All 4 direction. So that will give us the amount of water I can store. So let's see if this works or not. So if you are thinking to calculate the amount of water we can store here, right? So it's left max, down max, top and right max is 1, right? So that means I can store 1 unit of water here. Does that mean because my height is 0? No, that's not true. Why is that? Because here your water will get flowed. So here if you try to pour water, your water can flow from here. Your water can also flow from here. There are many possible options where your water can flow, right? So this is not valid, right? So this trick won't work this time because there are many possible options. Earlier, we only had 2 options. Why? What options? that water will flow from the left or water will flow from the right. But this time we got multiple options, so this trick won't work. Okay, so now let's see what we are actually going to do. So let's say we got this array, right? Now we have already talked about boundaries. So what's special for boundaries that every water, right? Every water, if every water flows, it will flow from the boundary, right? Every water will flow from the boundary. What I'm trying to say is, let's say you got water here, right? So it will of course flow from the boundaries, and boundaries can never trap water, right? Never store water. So what we are going to do, we are going to store our boundaries. Where we are going to store our boundaries? In a priority queue. Okay, let's now understand the approach. What we are going to do is store all our boundary, right, in a priority queue. Okay, why in a priority queue? Because what we'll be requiring is the minimum element, right? The minimum element. So let's see how our priority queue will help us. So I stored all the boundary elements. Now I need the minimum element. So I will get the top of the priority queue. The minimum in our case is 1, right? So now 1 will process its neighbors. So what are the possible options that 1 got for its neighbors? It's top, left, down, and right. Right? These are the possible options that can be 1's neighbor. So now let's see top. No, top is not valid because it is, you will get out of the matrix. Now left, it is already visited. So if it is already visited, right, as it is already in a priority queue, right? So that means we will also be requiring a visited Boolean array. Why is that? So we can check if we have visited it or not. So a visited Boolean array will also be required of same size of our matrix size. Right. Let me write visited here. Now let's see what operations we are going to perform. Okay. So we are at 1. So 1 possible neighbor is 13, right? And 13 is greater than 1, right? So imagine in tapping rainwater 1, what we used to do? We used to calculate left max and right max, and we used to get its minimum, right? So here for 13, let's say its boundary is 1, right? So can we store water here? No, we cannot. But what we can do is delegate our task. So I can't store. Now 13 will become part of our boundary. Okay. So 13 here will become part of our boundary. Let me use yellow pen. Okay. Now let's see. Again, with the help of our priority queue, we will get the top element, right? So the top element that is in our boundary. So what will it be? So as you can see, they're full of 12 and 13. So any 12 can be part. So let's say this 12, right? We get this 12. Now, see, this time the boundary element height is greater than its neighbor. That its valid neighbor is 10, as 12 and 12 are visited, right? So if that's the case, if boundary height is greater than what? Is greater than neighbor's height, right? If boundary height is greater than neighbor's height, that means water will get trapped there. Water will get trapped. If that's the case, so here, how much water will get trapped? So my boundary is 12 and my neighbor height is 10. So 12 minus 10, that is 2. So 2 unit of water will get trapped here. Now, so I know when water will get trapped here, when boundary height is greater than neighbor height. Okay. So now you must be wondering, there might be cases, right? When boundary height is different, right? So for that, we are also gonna do something more. We are gonna what we say, delegate our task. So now, as we know, our boundary height is greater, right? So we are gonna increase its height to 12 and we are gonna push it into our priority queue. Okay, now let's see what will happen. Again, in the priority queue, we are gonna get a top element and it will be 12, right? But here 12 will not work as its neighbors are visited, right? So here again we are going to check its also neighbors are visited, then eventually we are going to get this 12. Also this become your 12, right? This become your 12 now because this will also delegate tasks. It will increase your boundary. You are basically increasing your boundary. So now for this 12, its neighbors are 13, 12 and 8. The valid neighbors and 12. But all are visited except 8, right? And boundary height, that is 12, is greater than neighbor's height. So what will be the water you can store here? 12 minus 8, that is 4, right? Okay, so 4 unit of water you can store. Now what's your task? To increase your boundary, you're gonna increase it, right? And set it to 12. This will become 12. Now again, you're gonna pop element from your priority queue. It's going to be the smallest, it's going to be 12. Okay, so for this 12, again, it's safe, its valid neighbor is 4, right? So you are going to calculate and check if boundary height is greater than neighbor's height. Yes, it is. So it will be 12 minus 4, that is 8, right? So what will be the total amount of trapped water? It will be equal to 14. Okay, so now let's see one more example so that you completely understand it. Okay, so what was our first step? Our first step was to push boundary, right? To push boundary elements. That is our first step. So let's perform our task. So what we are going to do is to simply push the boundary elements. Okay, so we push the boundary elements. Now our second step, our next step. So our next step is going to be to extract from priority queue. To extract from priority queue. So it will be the smallest element. So what is the smallest element here? It is 1, right? So let's say this one. So as this one boundary is smaller, right? This one boundary is smaller than its neighbor. So we are gonna do nothing and delegate its task. It can't store water, right? So we are gonna simply delegate its task. Also, I would like to write one more thing here. Okay. So we discussed this. If boundary height is greater than, that means water will get trapped. What if neighbor's height is greater than boundary height, right? Greater or equal to. Then what we are going to do? Nothing. Simply delegate. Delegate means that increase my boundary. I'm simply increasing my boundary, right? Now, next step. Again, we are going to get element from priority queue. And this time, let's say it's this one. But this one, its neighbors are already visited. This one, its neighbor are already visited. Now let's try to get a 2. So this 2 already visited. This 2 neighbors are already visited. This is visited, right? Now we'll try to get a 3. So let's say we get this 3. Okay, so now this 3, its neighbor, that is safe. It's 1, right? So safe neighbor is 1. So what we are going to do is calculate its height. Our boundary height is greater, right? So 3 minus 1, that is going to 2. Now this is also become part of our boundary, right? This will also become part of our boundary and we are going to increase its height to what? To 3. We are increasing its boundary. Now again, we will try to get element from our priority queue. Let's say we get 3. Okay, this 3. So as it is greater, so 3 minus 2, right? Our boundary height is greater, right? 3 minus 2, it will be 1, right? Also, it is going to delegate, right? And its height will become 3. Okay, now again, if you try to get extract element from priority queue, let's say we get this 3 this time. So this 3 neighbor is 2 and 3's height is greater than its neighbors. So it will be 3 minus 2, that is equal to 1. It is going to delegate its task and also update its value to 3, whichever is greater. So the total water that will get trapped here is 1 plus 2 plus 1, that is 4. Okay, so now let's try to code it. Okay, so first n equal to height dot size, right? And then m equal to height 0 dot size. Now let's initialize our priority queue. So priority queue of pair type. Why pair type? Because we will be requiring to store its height, its row and its column. So int pair int, and now I want to tell my priority queue that sort on the basis of its height. So let's write code for it. Vector okay, and then greater its name priority queue. It's nothing, it's just to sort on the basis of its height, that the smallest element will be on the top. Okay, now what was our first step? Our first step to add all boundaries in our priority queue, right? So let's run a loop for it. And I equal to 0 is less than n, right? Then columns j equal to 0, j is less than m, j plus plus. Now when we push, if it's a boundary, so if I is equal to 0 or j is equal to 0 or I is equal to n minus 1 or j is equal to m minus 1. If that's the case, then I will push it into my priority queue. Priority queue dot push. First, the height, that is height ij, and what else? And the row and column, that is I and j. So I push it into my priority queue. Perfect. Now, what will be our next step? As we know, we will also require a visited array. So I will create a visited array here. Okay. So visit vector of boolean type. I'm going to call it visited, n size and vector. Cool. M and false. Initially it's false everywhere. I did nothing, just created a visited array, and here also I got a market true in my visited array. Okay, now that I have pushed elements in my visited array, what will be my next step? My next step will be to extract it. So while pq.size is greater than 0. Okay. Now, before extracting it, what I want to show you, that we know that we will be requiring a directional array so that we can move all the directions. So int, so let me create a directional array vector of int. I'm gonna call it directional. Okay, so the top direction the bottom direction, the top, the bottom, the left direction, the right direction. So these are the possible directions where you can move. Perfect. Now let's get priority queue. Priority queue, smallest element, right? So we are going to extract auto. I'm going to call it auto and my cell equal to priority queue dot top. And then don't forget to pop it. So now what I'm going to do is to get its height, its value, and height, its row and its column. So int h equal to height. Height is equal to cell dot first. What will its row? Its row will be equal to cell dot second dot first. And its column will be equal to cell dot second dot second. Okay. So now that we know the priority queue element, height, row and column, now we are going to traverse our directional matrix. I is equal to 0, I less than directional dot size. Okay. And I plus plus. So I'm going to call it int nr, that is new row, and int nc, that is new column. Okay. So int nr equal to directional, right, I and 0 column, and here nc is equal to directional I and first column. Okay. Now I calculated its direction. Now my task is to check whether it is safe, right? Whether we are not getting out of the matrix and other things. Let's see. So if nr is greater than equal to 0 and nc is greater than equal to 0 and nr is less than n, nr is neighbor row, okay, and our neighbor column is less than m. And now the important, what is it? If you have not visited it, so if visited nr nc equal to false, that means you have not visited it. So now what will be my first step? So it's a new row, it's a neighbor row, right, that you have not visited. So my first step will be to mark it visited, nrsc equal to true. Now let's talk about when our water gets trapped. So for that I'm gonna create a variable too in water, that is 0. So my water gets trapped when, let me write it here, to store my water plus equal to max of 0 or my height, if my boundary height is greater, right? So if my boundary height minus height of neighbor row and neighbor column, right? So if it is greater, just right, if my boundary height is greater, then decrease it. What's the difference? Will be the trapped water or 0. Now what will we do? Now we have to increase our boundary, right? So for that I got to push it in my priority queue. PQ dot push, what we are required to push is max of my height and height of my neighbor row and neighbor column, whichever is greater. Okay, what else? Simply the row and column, neighbor row and neighbor column. Okay, and whenever you get out of the loop, what we do is return water, right? Now let's check if our code is right. Let's review our code. First, after in water we created height, then we marked the boundaries, and then we created a vector. Okay, in the direction array we forgot to add our left direction, so it will be 0 and -1, my mistake. Okay, also here we forgot to update its direction. So what was it? Direction plus our current boundary row, right? So our row that we calculate in our column. Okay, so this is our overall code. Okay, now let's try to run it. Accepted. Now let's try submitting it. Perfect. So this was our question. What we did is first post all our boundary in a priority queue. Then we simply increase its boundary, right? And then we try calculate its height, and when we get its water when boundary height is greater than its neighbor height, right? And we always keep delegating our tasks so that we finally get our answer, right? Also, we were required to maintain a visited so that we don't go to a same cell again and again. So that's it for this video. If you liked it, do not forget to like, comment and share. Thanks for watching.